I think without further ado, I'd like to move on to Peter Challenor, if he's ready to give his presentation on uncertainty quantification. Peter,
okay.
Welcome.
Okay, so I'm going to talk about uncertainty quantification. And start off, I'll define it because people do use that phrase in different places, and it's not the best phrase to explain what we do. So basically, when I say uncertainty quantification, what I'm talking about is the statistical analysis of complex numerical models. We had an I&I program on this a couple of years ago, and in the UK, we have a lot of expertise. So we've had people on the Alan Turing Institute, Exeter, Durham, Sheffield, Southampton, UCL, and there are other smaller groups around the country. We're keen to help on epidemiological modeling and quantifying uncertainty on epidemiological modeling. We did self-organize and apply to RAMP, but we really didn't get any response. And I hope that doesn't mean that RAMP isn't interested in uncertainty. Don't want to make a big deal out of that. There are applied maths groups who do something similar, but they do slightly different problems. And I'm going to talk about the statistical aspects of uncertainty quantification rather than the applied maths engineering type. So we have some model, and I'm just going to write that as y as f of x. So f is a million lines of code. It could be for climate model, ones we've worked with. It might be shorter than that, the sort of some of the models we've seen. And f can be a deterministic model or a stochastic model. Doesn't really matter. Well, you change what you do it. And we're going to treat f of x as a black box. I'm not going to clamber inside the model and change it in any way at all. So you could give me your model or let me run your model and I could do the uncertainty quantification without knowing what's inside it or messing about with what's inside it. So we're doing what's called non-intrusive uncertainty quantification. We don't touch your code. Your code stays the same. Now, uncertainty is often split into two types: aleatoric uncertainty, which is random stuff, and epistemic uncertainty, which is the uncertainty comes from the fact you don't know things. And stochastic models, their stochasticity, if that's a real word, gives you aleatoric uncertainty. This is just random stuff. There's nothing you can do about that. It's just the way it is. But not knowing things, like not knowing what a value of a parameter is, being uncertain about a parameter, is epistemic uncertainty, and all models have epistemic uncertainty. And all our methods have stochastic versions, but I've only got half an hour, so I'm not going to talk about the stochastic versions of our models, but we can deal with that aleatoric uncertainty. So if you've got a stochastic model, it doesn't mean we can't do the things I'm going to talk about. It's just a little bit more complex. So the epistemic uncertainty, unknown inputs, parameters, initial conditions, boundary conditions. We don't know those, or we rarely know those. They are uncertain, and we want to know how that uncertainty propagates through this complex nonlinear model. But then there's another source of uncertainty, which is, I actually think, more important, but much harder to handle, which is what's often called structural uncertainty, the difference between the simulator, the model, and reality. And I'll often talk about the model as a simulator because I'm going to talk about modeling models and it gets confusing. So the simulator is the epidemiological model, okay? And there are approximations and there are parameterizations, there are numerics that mean it's not, the code is not doing exactly what the equations would say, and the equations themselves are not the same as reality. We don't live in a mathematical model, and we have to take that into account. So why should I care about uncertainty? Well, honesty. We should be honest that our models are uncertain, they're not perfect. In the last talk, there was some talk about reproducibility. If two models give something similar, are they doing the same thing? Without uncertainty, you can't say. You don't have a metric to compare models unless you have some measure of uncertainty. we should be rigorous. We should be honest and rigorous. And it also helps you think about your models. If you do a sensitivity analysis, and I'll talk about sensitivity analysis later, it starts to think about what's important in the model. And we often find with models we work with that some processes people think are vitally important turn out to make no difference whatsoever to the model. So it helps you think about the model. It gives us tools to deal with ensembles of models and hierarchies of models, which I'll come back to at the end. So the traditional way to do uncertainty quantification would be Monte Carlo, Markov chain Monte Carlo, or quasi Monte Carlo type methods. So you sample from your inputs, you propagate that through your model, and that would give you a sample of the output distribution. And that's really nice. But if your numerical model, your simulator is expensive to run, we can't afford to do that. We need thousands of runs to build up a distribution using Monte Carlo type methods. So the alternative to doing Monte Carlo on the numerical model is to build a cheap surrogate model, a fast model of the model, a model of the simulator, which I'm going to denote by F tilde. And I'm going to particularly talk about emulators rather than surrogates, because I'm going to define an emulator as a surrogate model that has a measure of its own uncertainty. So it tells you how well it's doing. It's an interpolator that tells you how well it's doing. And we use what are called Gaussian process emulators. So the surrogate model we fit is a Gaussian process, and a Gaussian process is simply an infinite dimensional analog of a Gaussian distribution, or a Gaussian distribution of functions. And doesn't mean we're assuming that the inputs and outputs of our models have a Gaussian distribution. The Gaussian process part refers to the uncertainty in our fitting. So let's just look at a Gaussian process. So here we've got a true function in black. Here it is in black, which I hope you can see that. And then we run 1, 2, 3, 4, 5 runs, and we fit our Gaussian process, and the mean of the Gaussian process is the blue line, and the uncertainty bands are given by the dotted line. So that's 95%. Someone's asked a question. Have they? No. Okay. So 95 bonds, but you have to think of the Gaussian process itself is a function. So we have thousands of lines going through here to define that envelope. And okay, that gives us an error. And if we want to reduce the uncertainty, we just run another point, and that uncertainty collapses down. So we can control the uncertainty on the emulator. Emulator has uncertainty everywhere, but it's under our control. And if it gets too large, we simply do another model run, and that will reduce the uncertainty. So this is the uncertainty under our control. So what procedure would we use to set up an emulator for a model? Well, we'd set up some priors. So one of the things I didn't point out was there's a mean function sitting under here. There's a mean function, a zero mean Gaussian process here. I think there's a linear function sitting under there. So we'd set up what does the mean function look like. We'd set up priors on all our hyperparameters. And then the important part that I'm not really going to talk about is we design an experiment. And we need to fill space to run our model everywhere, because we're going to build an interpolator, and that surrogate, that interpolator, has to be good quality across all of space. So if you let me run your model, I'll run your model in places you've never run it and have never thought of running it, and I will often break it. We then run this simulator ensemble, comes out of the designed experiment, and then we build an emulator, and we generally use Bayesian methods. You don't have to, there are non-Bayesian methods, but certainly in the UK, we're a very Bayesian community. And then another important part is we validate that emulator. It's quite easy to build bad emulators. It's quite hard to build good ones. We validate it. If it doesn't validate, we go back and check, is there something in the prior that's wrong? Or do we just need to do some more runs? And then we circulate around here until we've got an emulator that validates, and then we can start to do things with it. So what can I do when I've got my emulator? Well, I can do prediction. I can predict any point what your model is going to tell you. With some uncertainty, but I know what that uncertainty is. I get an uncertainty bound. I can also do sensitivity analysis and uncertainty analysis, and I'll just give a little bit more on sensitivity analysis. So which inputs are the outputs sensitive to? And if you're going to do an uncertain sensitivity analysis, I know a lot of people do sensitivity analysis, please don't do one at a time. Sensitivity analysis, just look at the main effects. You're not looking at the non-linearity in the model in that case, and certainly the variance-based sensitivity analysis we do, which are very similar to analysis of variance, we would look at main effects and certainly two-way interactions and possibly three-way interactions, and that starts to tell us a lot more about the structure of the model, and not simply which are the important parameters, but which are the combinations of parameters that are important, and that's telling you a lot about the non-linearity of the model you may not even appreciate from just writing down the equations. Uncertainty analysis, we put a joint PDF, sometimes called a prior, though it's not really a prior, on the inputs. And what is the statistical distribution of the outputs? As we propagate that distribution through the model, what do we actually get as a distribution on the outputs? So we can do Monte Carlo with the emulator, and there's a sort of balance of uncertainty here because our emulator is itself uncertain, but we can control that uncertainty in the same way with a Monte Carlo. You control uncertainty by the number of runs you do, but by building an emulator, we can do vast number of runs because it's very cheap, even though we've added that extra uncertainty from putting the emulator in, and we can get much better answers than you can simply by doing Monte Carlo on a model that isn't trivial. Some cases, some special cases, we can use the Gaussianness of the Gaussian process to do that analytically, but you have to be in some fairly special cases to do that. Okay, what I want to spend the next 10 minutes talking about is calibration, tuning, estimation, inverse modeling. Given some data on the model outputs, what can we say about the model inputs? Can we estimate the parameters given data? And traditionally, you do this with least squares or maximum likelihood or Bayes, but we have to take into account the model discrepancy. The fact that the simulators are not the same as reality. I said before we have these structural errors, and that means that we're not simulating reality, and when we compare with data, we have to take that into account. If you fit to data without including a discrepancy term, you almost certainly overfit. So the classic way from something in the 2000s, I think it's 2001, Kennedy O'Hagan came up with a really good way to do this, which has two Gaussian processes. One's an emulator for the simulator, and the second Gaussian process, which you fit at the same time, fits this discrepancy between reality and the simulator. Reality as represented by the data. We can never get a handle on reality itself. We only get data. So we have simulator, we have data, and we fit two Gaussian processes together. That's good for prediction, where we only need the sum of those two Gaussian processes, but there are horrible identifiability problems of trying to fit two Gaussian processes at the same time to the simulator and the data. There are ways around that if you have very strong priors on your model uncertainty, and on your discrepancy. So you can be done, but it's difficult. So I'm going to talk about an alternative, which is known as history matching. And the idea of history matching is instead of trying to find the best sets of parameters, we don't try and find the best parameters, we try and find all those sets of inputs that are implausible. So we find all the simulators that don't fit the data, and the one somewhere in the bit that's left is the one that fits the data, is the best fit. So we throw away all the bad fits and find what's left, and we can then do a Kennedy-O'Hagan type estimation or calibration in that tiny bit left if we want to, but it maybe we don't need to. So how do we do that? Well, we set up what's called an implausibility measure. So this is the data, the observations, and we have some set of inputs, X, and we're looking at those inputs to see whether they fit the data, and we just take the squared difference between our emulator, or the expected value of our emulator, and the data, and we scale that by these three variance or mean square error terms. They're probably better to think of them as mean square errors. There's the emulator variance, we know that from the emulator. The observation variance, how good is our data, which normally we know, how we have some handle on. And then there's a term here, a discrepancy term, that says how far away we expect the model to be from the data. This is saying about this model discrepancy. We don't think our model's perfect, so there's an extra term we put on there that takes into account that error in the model. So we calculate that implausibility measure, and we can calculate that in any set of inputs. So to do a history match, what do we do? Well, we do the same thing before. We run our simulator in a designed experiment. We build and validate a Gaussian process emulator. We calculate the implausibility using that formula I've just shown. At all points with implausibility greater than 3, we rule out to be implausible. And why 3? Well, if you look at this, if you assume that this had a normal distribution, you use 2, 95%. But Puckelsheim, in a paper in 1994, shows that any unimodal distribution, the 95% limit is 3 or less. So it's a conservative way of ruling it out. And what remains, we term not ruled out yet space. We will rule it out soon. And then we do this again and again. So we take our not ruled out space, we do some more runs of the model inside that not ruled out space. That gives us a better emulator. If we have a better emulator, this term reduces, and we zoom in on the ruling out more space at a time. We zoom in on where the model and the data, the simulator and the data are similar. And we repeat that until we reach the stopping rule. Here's an example. So here is a model, and the black line is the truth. That's the true model. And our data point is this little cyan point here with some uncertainty on it there. And we run our model 3 times. We build an emulator with uncertainty, and you can see down here our implausibility. And there's 2 places, 2 areas where we don't rule it out. We don't rule them, and we don't rule them all out here because it's close to the data. The implausibility is saying it's close to the data. Out here, we don't rule it out because we're uncertain about what's going on. We don't know enough about what's happening to say the data can't fit here. We do another couple of runs, and now the uncertainty here on our emulator has collapsed enough that we can now rule out this region, and the only region we've got left is here. And in fact, improving the emulator won't help here. Almost all this uncertainty is coming from the uncertainty in the data. So that's a trivial example. Let's look at a non-trivial one. This is a model of the human heart. It's modeling 1 beat of the human heart. It's a 6-hour runtime. We did some pre-processing to reduce the dimensionality I don't want to go into. Initially, the modelers told us, oh no, there's no discrepancy. Our model is perfect. And if we did that, then the not ruled out yet space is empty after the first wave. The model just doesn't fit. So we went back to them and they said, oh yeah, well, yes, this isn't right and this isn't right in the model. And so this is the result after wave 1. So 25% of space remains, 75% doesn't fit, and this is a very complicated diagram. We have 20 inputs and they're across the top. 2 of the inputs turned out were the same, so you get a little straight line there, and that's 2 of them actually being the same. And what you see down the being diagonal is the marginal of this NROI space on 1 dimension, and up here this is a 2-dimensional look into 20-dimensional space. So there's 18 dimensions behind, and this is the probability of finding a point if you go back down that point. So here there are very few points in those 2 parameters that give us anything like data. If we then go on to the next wave, it's starting to become much more discriminatory. Only 6% of space remains. I'm not going to go through all these. You're not cardiac modelers, you don't really care, but you can see here we've done a lot of discrimination here, some discrimination here, and we're starting to see there's some twisty manifold in 20-dimensional space. And wave 3, that should say 5%, not 55%. We've gone from 6% to 5%. It wasn't worth going any further and doing any more model runs, but we've reduced space down to a small proportion of the original space. So what do we do for these stopping rules? Well, we shrink to some pre-specified value, and then we do Kennedy-O'Hagan. Often people don't do the Kennedy-O'Hagan, they do the second part. NROI becomes so small, we effectively use it as a point estimate. It's tiny enough that the model isn't changing as we go over that. The other interesting one is the NROI disappears completely. And that means the simulator and the data are not compatible. You couldn't get that data from any input of the model. And that means that the model, say the model and the data are completely incompatible. If you do a classical calibration, that won't happen. Classical calibrations, a classical estimation will find you the nearest point to the data. And sometimes you want to say, well, no, this doesn't fit at all. And a straight Bayes or maximum likelihood will not tell you that. If we do shrink NROI to 0, we can actually bring it back by making that discrepancy term larger and larger. And you can think of that as a tolerance to error. How bad are you prepared for your model to be for it still to be useful? And that's a useful conversation to have with modelers and decision makers. Your model doesn't fit the data, but if we're prepared to accept that, how much error are you prepared to have? How much discrepancy between the data and the model are you prepared to accept? Okay, that's been a whistle-stop tour through uncertainty quantification. Things I haven't really talked about: stochastic models. There are stochastic versions of everything I've talked about. We have one of the ways when building an emulator is you emulate the stochastic part separately. So we have 2 emulators, an emulator for the mean, which is the one I've shown, and an emulator for the variance. We can do similar things with agent-based models. We have methods for estimating that discrepancy term. Everyone's always worried about that. We can work with hierarchies of models. So if you have a spatial model, you increase the resolution to make a more expensive model. We have ways of doing inference up and down those hierarchies. We can deal with multiple models of the same thing. So if you have 3 models of the epidemic and you want to compare them, we have ways to do that. Someone yesterday talked about value information. We can talk about value information. We generally don't do data assimilation, but some of the epidemiological models, data assimilation, where you put data in, where the data is put in time and you pull the model back towards data dynamically, might be interesting. So we have a statistical UQ community, probably one of the best in the world, and we want to help. In Exeter, we've started working with Leon Danon's MetaWards model, but if anyone else would like help with using these methods, would be very pleased to help you do uncertainty quantification, particularly if you've got an expensive model and you can't do Monte Carlo. Okay, thank you. I think that's it. Yeah.
Thanks very much, Peter. We have time for maybe a couple of quick questions. Who would like to ask a question? I think it's probably best just start because I can't see the whole, if you do, because I can only see some of the participants at any one moment. Do you have any quick questions? Well, if not, you can go and make yourself a cup of coffee and think of some questions, and we can take them forward in the discussion section at 11:45. So we'll reconvene to 11:15 for Stephen Riley's talk. Thank you all very much. Thanks to the speakers.
Thank you.